Hello everybody, in this video we're going to try to explore the relationship between length, area and volume when we start to enlarge things and change things with different scale factors. So first of all, if we have a line, let's imagine a line, it's not a very straight line, but let's say that is 2 centimeters, and I enlarge it with a scale factor of 3. All right, SF for scale factor. Then, of course, okay, my line gets bigger and it is now 6 centimeters. But what about now if we think about a little rectangle, and this is 2 centimeters by 3 centimeters? What would happen if we enlarge that by a scale factor of 3? Well, when I say scale factor, I'm talking about what's known as a linear scale factor, which means it's just going to change the length of the sides. Okay, so if I have a new triangle, well, clearly I'm going to have 6 centimeters along the side, and I'm going to have 9 centimeters there, look, along the top. Now, so far we haven't really thought about area, but the original area of the first shape was 6 centimeters squared, and the area of this new rectangle is 54 centimeters squared. So you can clearly see that the area has increased by a scale factor that is certainly bigger than 3. Okay, I'm going to now refer to that original scale factor as the linear scale factor. Let's think about what an area scale factor might be. Well, I've got to think, how do I get from 6 to 54? What am I multiplying it by? And of course, if I do 54 divided by 6, I'm going to get 9. So my area scale factor was 9 when my linear scale factor was 3. Let's try this again with a different scale factor. Perhaps we could start with the same triangle. We've got 2 centimeters there, look, and 3 centimeters there. And this time, let's enlarge that with a linear scale factor of just 2 and see what happens to the area. So if I do that, my new rectangle will be 4 centimeters by 6 centimeters. So it's going to have an area of 24 centimeters squared. My original rectangle had an area of 6 centimeters squared. So let's work out that area scale factor. What will my area scale factor be? Well, in order to get from 6 to 24, I need to multiply by 4. So my area scale factor is 4. So can you see a pattern between the linear scale factor and the area scale factor? Well, there is a pattern, and if we have that linear scale factor and square it, we can work out the area scale factor. So if we call the linear scale factor L, okay, then L squared is going to be the area scale factor. Okay, but we can extend this even further. Let's think now about volume as well. So let's start off a brand new example. Okay, let's think about a cube, perhaps. Okay, so we'll start off with a square. Okay, so let's say this square is 3 centimeters by 3 centimeters this time. Okay, and we are going to have a cube. We'll start off with a cube that is 3 centimeters by 3 centimeters by 3 centimeters, and we're going to increase it with a linear scale factor of 2. So that means we're going to have 6 centimeters by 6 centimeters by 6 centimeters. So let's see if we can work out these volumes now to work out how much this volume has increased by. So if I do 3 by 3 by 3, then I'm going to have 27 centimeters cubed as my original volume. If I do 6 times 6 times 6, I'm going to have 216 centimeters cubed. So now if I do 216 divided by 27, I'm going to have that volume scale factor. And the volume scale factor is 8. So is there a relationship between the linear scale factor and the volume scale factor? Well, yes, there is. If we call the linear scale factor L, then L cubed is going to be the volume scale factor. Okay, so this is what's happening. When I enlarge a shape with scale factor 2, its area will get 4 times as big, its volume will get 8 times as big. If I increase a shape size with a scale factor of 5, then any area will increase by a scale factor of 25 and its volume increase by 125, whatever that original number was cubed. That's how we can work between length, area, and volume and think about enlargement.